Welcome everyone. We now start talking about the numerical example for do affine scaling algorithm, and this is this example is in lecture 11, numerical example online and on Canvas. We're going to using the same problem we have in previous document, and it's just using his do problem. Okay, his do problem is maximization problem, 15 times omega 1 plus 15 times omega 2. So I have two constraints in the primal formulation, then I have two do variable in the do formulation. But I have four different constraints in the do models, and then we have the C vector actually becomes right-hand side. Okay, and this is what we have. So we're going to start to the algorithm illustration. Well, we're going to start with the omega naught equals to negative 3 and negative 3, S naught, which is initial do slack, equal to 1133. Based on the algorithm we have in the do affine scaling algorithm document, lecture 10 on Canvas, we're going to follow exactly this last page, the do affine scaling algorithm. Find the omega naught and S naught satisfying the do constraint, and S naught is strictly positive. We can calculate the capital XK equal to the diagonal of XK, and calculate the do direction, d omega and ds, based on these two formulations. And we check for unboundedness, okay, and then we compute the primal solution over here, primal solution. Then check if it's an optimal condition satisfied, the duality gap getting real close, and primal solution is non-negative. Then we know we have optimal solution. Otherwise, we can need to calculate a maximum possible step size equal to alpha times SIK divided by negative DSIK, okay, when DSIK is negative. So alpha equal to 0.99 in our example. Update the do solution and the do slack and go back to step 2 to calculate the do direction. And we're going to follow this exactly using illustrate this example for now. Okay, so also I'm doing this just to be consistent with the Excel spreadsheet I'm going to show later on. So S naught, capital S, with the diagonal of S, and times A times S negative 2, negative square, inverse square, and calculate A times S naught, negative square, and times A transpose inverse. Then I can calculate d omega using this times B. That's it. And do slack direction ds is the same thing, negative A transpose times d omega, and can be easily calculated. Since all four of them are negative, and we want to maintain do slack is non-negative and is actually strictly positive, so we need to have some restriction on my step size. After calculate d omega and ds, I can calculate the primal solution, corresponding primal solution. Negative S naught negative squared times ds, but you can see right now x is strictly positive already for all of them. For all x naught is all positive. Then I can calculate the duality gap equal to 54 something. Is far bigger than 0. Therefore, we need to move forward with this. Okay. So we can calculate, since all four components in the ds are negative, we have to calculate one of them, which one is the smallest. So this one apparently is the smallest and among those four. Okay, equal to 0.04207. That's my maximum step size. Based on this, I can update my new do solution. Okay, update my do slack in that case. All right. So iterate again, putting the new do slack into the diagonal, capital S, calculate d omega, new d omega, calculate the new direction for do slack as well. Still, all four components are negative. We need to have some restriction on the step size. After I have a d omega and ds, or after I calculate do slack direction, I can update my current primal solution. The primal solution x1 is strictly greater than 0, and the duality gap improved from 54 point something to 9.8 something. So, but still, we need to calculate a limited step size among all these using these four. Okay, and the largest step size we can allow is 0.1391, and using this to update my new do slack, do solution omega and do slack s. Then we can calculate corresponding x2 later on. I will show you in a second right here. Put in the s into a diagonal matrix. Okay, and calculate the new do solution, do direction, and do slack direction. Still, all of them are negative, and so to speak. I can update my primal solution in this case. Okay, 29.99. So it's eventually going to converge to 30. This is 14.9969 is going to converge to 15. These two are going to converge to 0. At this point, the duality gap converge to points 0.3723. This is smaller and smaller, and still we can have to calculate the step size based on these four. Okay, and update the third iteration, the do solution and do slack. In that case, we can calculate the current duality gap converged, kind of reduced to 0.0652. So we can carry this a couple more iteration, and this is the optimal final do solution, do slack solution, and primal solution. And the objective function value stay the same, -45. So we can easily illustrate this. Again, for the do affine scaling method, we illustrate a version of a big M method and two-phase method to discuss how to find the initial feasible do solution. But this numerical example, we're just giving you a particular feasible solution to start with. Okay, so welcome to walk through this in detail, and I thought it's going to be helpful. Next, we're going to come back to the same problem using a Excel spreadsheet. See how we implement it. Very simple, using the same problem. This is my A, and right-hand side, and the cost coefficient vector. And starting primal solution, do solution, and do slack, and calculate the current duality gap. Putting the do 1 over S on the diagonal, okay, 1 over S on the diagonal, which is S inverse, basically. and calculate the A times X inverse square, A times S inverse square, okay, times A times S inverse times A transpose inverse in that case. Sorry, I think I have a typo here. It's actually S and -2. In that case, all right. And after I calculate this, I can calculate d omega, ds, update my new primal solution, and check my magnitude of the due slack direction, and make sure this is due constraint is feasible. So all these are 0. A transpose times d omega plus ds equals to 0. Okay, so this is then based on this, I can calculate what the corresponding step size and choose the minima positive one, using it as the step size for all the coordinate when we update x's. Okay, so here we can calculate update the due solution based on the step size, due slack based on the same step size, and x is pre-calculated already over here, so I just copied it over. And this is my new duality gap, basically equals to the primal objective function minus the due objective function. One more step, okay. Since I have the new due slack, I put in the S inverse right here, A times S inverse square right here, inverse of A times X inverse square times A transpose inverse, and that's the purple area. Based on this, I can calculate the d omega ds, and once I have ds, I can calculate the primal solution and double check the magnitude of ds. Okay, and as you can see right now, and x is converging really quickly to 1, 0, 0, and 0 already, and ds becomes fairly small. And the step size becomes a little bit large, almost 100, 99.028. And I can update my primal solution. It's copied directly from here. The due solution using the step size right here. And this, the due slack also based on the beta times ds. And you can see that my duality gap converge pretty small already, even as in the second iteration. So due, affine due solution is converge much faster than the other primal affine scaling method. In this particular example, only take no more than 3 iterations. We have very good convergency. This is not always happen, but this is nice to see that with this particular problem, it converging so fast. Okay, and this pretty much I follow the step for this document from the theoretical development of a dual affine algorithm in the last page, and I using a lecture 11 numerical example, walk you through 3 iterations for a numerical example, using a fairly different example to begin with. Then I'm using a separate example, different numerical structure, to show you the Microsoft Excel implementation. You're welcome to change this problem using the data in 7.2 and see if you can get a good convergencies as well. All right, and just exercise how to use that. So you get familiar with the algorithm. This will conclude my this lecture period for go over numerical example and Excel spreadsheet using the dual affine algorithm, and Next lecture period, we're going to spend two small lecture talking about primal and dual affine scaling method using numerical example and a Microsoft Excel example as well. We'll see you in the next lecture.